How y'all doing? Amazing. Heck yeah. All right. How's everybody else doing? Okay. You guys haven't gotten stressed out by the semester yet, so everything's fun and games still. I'm glad to see most of you have returned. Hopefully those who didn't have found something better to do with their time. Before we get too deep into it, so I want to keep talking about the solar structure today. Again, if we can't make sense of our own star, what chance do we have of making sense of the rest of the galaxy and the universe at large? So we're going to keep digging into that and try to make sense of the details and the mysteries of the sun a bit more. Probably for a few more classes, honestly. So I'm going to take my time with that because I think it's just so important. So we'll pick into that a bit more today. Before we get going, does anybody have any technical problems that they think other people might want answers to as well? Have you all been able to access the Moodle all right? I see some people have already started posting videos, so it must be working more or less for most of you. Are we good on that for the most part? Yes. Okay. I'm also going to try to get some attendance points in here too, so I want to review what we did last week. But before I get to that, I thought it might be interesting to motivate our study of the sun a little bit more. So this is a book I brought in last semester a little bit. It's called Native Science by Gregory Kahete, who is, I believe he's a professor at Harvard. I'm not sure if he's still there, but it's a really cool book that talks about the different ways that the Navajo people looked at the sky traditionally. And there's kind of a cool lesson buried in here about what the heck we're trying to do in astronomy in general. So obviously in the West today, when we think about the stars, we're mostly thinking about physics and how they do the magic that they appear to do. And that cosmological question of what it means to us has been a little bit swept aside. And that's a bit unfortunate in some sense, because there doesn't seem to be a great place to talk about those things anymore, at least inside of an academic setting. So I thought I'd just read a little bit of this and then sort of riff on how that might relate to what we're actually even doing in the physics side of things as well. Because aside from the obvious technological implications of understanding the sun, I talked about fusion a little bit last time, which is obviously cool. But there's something about science and this idea of understanding how stuff works that seems to sort of happen before we even think about what we're going to do with it, right? There's plenty of scientists that just study the nitty-gritties of nature without any real technological application, right? There's people who study bugs and birds and bees, and people who study little bacteria. Oftentimes as a scientist, you end up trying to make the case to the people who give you money that this is going to solve some disease or it's going to lead to this new energy revolution or something. But there's something about the reason that we study nature that has nothing to do with actually anything practical. And there's something about it. There's something we really fundamentally value, just understanding how things work. So let's think about that a little bit. So I'm going to read this little passage. So this is the Navajo tradition, and we're talking about the role of the sun in this society. And this has all come down through oral tradition. So, they write, the holy ones decided that the sun, considered to have male characteristics, would provide order to the days and seasons. And so the seasons are, of course, recognized by the location of the sunrise. Referred to as the day traveler, the sun is used to determine time in a general sense, as well as to determine the cardinal directions. The equinoxes and solstices are considered sacred times of the year, the end of the sun's journey, marking the passage of time and seasons. Ceremonies are held to ensure the actions of the people and the earth are in harmony. At these times, it's said that for thousands of years, the sun, moon, planets, air, water, and electrical forces have aligned themselves at these times. Universal alignment where energy is shared. And so this general pattern seems to have played out not just in the indigenous traditions, but if we actually go on, this is that book, by the way, in case anybody wants to check it out, highly recommend. But all across the globe, we go back. So this is actually an artifact found, I think, from about 3,500 years ago in Norway. Very famous artifact. People have set the sun at the center of their cosmologies forever and ever, all around the globe. It's essentially the deities that are associated with the sun are often the supreme deities. You see this in Egypt, you know, and the question is, and all of these deities, again, are associated with this concept of order, right? So I guess the question is, something to put to you. Why? Why do people care so much about the sun going back? Why do they associate it with this order bringing force? Right? And the Navajo tradition, it's associated with this masculine energy of ordering things. Why do people care so much about order? Yeah, please. Tell me your name, by the way, so I can give you some attendance points.
Consider the sun so great and powerful is because it's what helps the crops grow. It's like a symbol of life to people, and it's what keeps us alive.
Yeah, I mean, obviously, maybe not. It's so funny because today, obviously, all of the energy that we have on Earth comes from the sun, essentially, right? And if we, there is some heat below our feet in this molten crust, and there's some reservoirs of geothermal energy, but for the most part, all the plants, all the food we come from, our bodies are built out of, it all comes from the sun. And it seems like people recognized that thousands of years ago to some extent. What about this aspect of time and order? Yeah, tell me your name.
I guess so. It's a constant thing. Like moon has its phases, and you can't always see it all the time. Sure, like clouds and stuff around the sun, but if you think about, there's this giant ball of light and stuff in the sky that we can always see, that always provides some unity, and we always know it's going to be there pretty much, then it could help represent order and just.
Yeah, I think it's a perfect symbol. It shows up in the same place every day. Well, it wanders, but every year it's going to come back to the same place, right? It's going to rise in a slightly different location. And I think, honestly, that there's something about us. Like, one thing that's really funny is I noticed that almost all of you have sat in the exact same seats that you sat in last time. I don't have a photographic memory or anything, but there's something that we really like about regularity. It really gives us comfort, right? And if you're trying to find something that's comforting about the natural landscape, there's really not much more to it than what's happening in the sky. And the sun is obviously the brightest thing in the sky. So there's something really profound about that. Does anybody else have any thoughts on that to contribute? Yes, tell me your name. That's right.
Another thing with it being constant is that we've been able to rely on it to keep us alive, in the sense of, like the book said, cardinal directions and keep track of time, and tracking like hunting seasons and stuff like that. So in the past, when we had to rely on that, it is that order and that consistency has helped us with survival.
Yeah, I'm glad you brought that up. Orientation's a really super useful skill for everything, right? If you want to tell somebody, I found this herd of elk, and you want to tell them like where to go, how are you going to point that out on a landscape, right? It's like, well, you could say like you got to go past these trees over here, but that could get confusing. But the sun, it's always there, and you can follow it each day, right? And that'll, I can't think of anything more reliable than the location of the sun. Of course, there could be clouds if you're looking at stars or something like that, but the sun, you can even see it through the clouds. So it's quite useful. Please.
Yeah.
Mia, hello.
It also adds the aspect of light. Like during the day, it's easy to be structured and you can control more. But if it's dark, there's a lack of clarity.
Oh, that's good too. That's a really good point. Yeah, it's like darkness too is like the oldest poetic metaphor, right? For like, the worst possible situation is where you can't see what's happening, right? I think we're fundamentally defined by our visual nature too as human beings. There's something about it, right? I always point out, and I'm stealing this from Julian Jaynes, who was an incredible psychologist back in the 19th century, but he pointed out that the words that we use for intelligence are all related to sight, right? If you're like, that's a brilliant idea, it's like, that means bright, right? Or how about just a bright idea? Or if someone's explaining something to you, you're like, oh, I see what you're saying. But like, you don't actually see anything, but that's the way that we think, right? Is in terms of light and color and luminescence, right? And the opposite of that, confusion and chaos, it's all related to darkness and the absence of that sort of clarity. So that's a really good point. Yes.
Aiden, um, I think it could be structured with, to follow up with what you said, that fire, when the fire was made, it was described as life. And the sun is what they thought and prescribed was a massive ball of fire.
Yeah, so fire is wild too, right? Because if you look at a piece of fire, it dances around, right? And it has so much power, it can consume things and so forth. I don't know which I'd have to do some more research to see which traditions associate fire with life, but it makes complete sense to me, and I have seen that before for sure. Yeah.
Divorced as a society from the natural world now, but hundreds of years ago we weren't as divorced from it, and all of the flora and fauna depend on the sun for their instructions for everything from eating to hibernation to when to procreate.
Everything, yeah.
And we depend on the flora and fauna for everything. So what the sun is doing informs of when the salmon are coming or when the locusts are coming. We need to know.
100%. And like this, we got really into this last semester because we were more looking at the location of the planets and the stories that were told alongside of that. But look, people didn't have Netflix, right? You know, without all of our evolution, people would, I'm assuming, you know, I could be wrong about this, but I think most people were probably sitting around campfires at night for hundreds of thousands of years, looking up at the sky and telling stories that reflected their experiences in their daily lives with emotions of these things too, right? And of course, not so you're mentioning that there's a practical side of that too, right? Absolutely. But I think there's also just like an almost, you know, there's some like, why do we love Netflix? Like, that's a good question. Why do we like, why do we like stories so much? Like,
I mean, they were really
that's part of it. Entertaining. Yeah, for sure.
You know, in the modern sense, we still have work, we still have school, but a lot of times they're could be snowed in for months at a time. So, I mean, I think it's
part entertainment. Yeah, in the back. Tell me wait, one second. Remind me your name again.
Isabel
That's right. Yep.
demonstrates human emotion.
Or in Shakespeare, like it portrays history.
Yeah. Both of those are important. So you can pass along something like some memory of something that's happened already, right? So if you know you've been through some terrible circumstances and you found your way out of it, you can pass that on to the next generation. What was the other one? Emotions too, right? So this ability for us to all relate to one another too, that's really nice. So if we have some shared story, then maybe you're not so different from me because you felt that before too. And that's really useful because now I can trust you because in some sense I see myself in you. So that's interesting as well too. Yeah, give me a few more thoughts on this. Tell me your name. Courtney.
Learn other things about what could be versus what might.
Yeah, you don't have to live it out, right? You don't have to be stalked by the serial killer in order to learn how to avoid that situation, or you know, you might scale it down into your own mundane level of existence. But yeah, you can live out these realities without having to actually subject yourself to the danger or the heartbreak or whatever it is, right? So, that a lot of that gets lost, and especially as we, you know, we have to really wrestle with some really nitty-gritty physics questions here. But in some sense, there's something very congruent with what we're doing here in physics by trying to tell a story about how the sun works. Because the best stories that we tell in science are the ones that can be explained to somebody else and can be transmitted on. In other words, they should make sense, right? And so how is it that we end up with one scientific theory versus another as the years wind on? Well, the reason is that the story we've been telling starts to break down over time. It fills up with holes, right? You guys ever watch a really poorly written Netflix show where you're just like, that doesn't make any sense. Like how did, I can't think of a great example. I try to avoid terrible shows, but it's like oftentimes you'll just see these plot holes, right? And the same thing happens with the scientific theories that we tell. And they're eventually replaced by better ones that actually hold up, given the more information that we have, right? Better telescopes, better instrumentation, just more people working on the problems. So there's something really similar going on with this physics process. So we'll get back a little bit more to the methodological side later. I want to definitely pivot over and keep picking at the structure of the sun a little bit more. But while I have you all talking to me right now, why don't you guys try to remind me of what the heck happened last class a little bit so that we can make sure we're all on the same page? Yes, Jasmine, right?
About a lot of stuff, but one of the was like ions and how the sun has like ions in it, and we went through like nuclear energy and kind of like talked about like how like
Let's just stick with one of those right now. So ions and plasma and so forth. Does anybody want to expound on that a little bit? What's the story with plasma and ions? Why would we even bring that up? Anybody remember? Yes.
Talking about the structure, like how we recognize things and they're not actually. I don't.
Okay, it's okay. It's so important that this is why we're doing this, because we need to make sure that if you walk out of this class today, you at least understand this one important point. Plasma, ions. Maybe I didn't get into the plasma thing enough as well as I should have, but I read you guys at the beginning of class a little excerpt, I think it's from the first page of your textbook, that says essentially that the sun is this ionized ball of gas, right?
About how the blackbody curve of the sun's light doesn't align with ionized gases blackbody curve.
Yeah, exactly. What was her name?
GOT.
Geo. That's exactly what I'm kind of driving at here. So when you ionize the gas, like in these lights up above your heads right now, you actually develop this. Oh, I got a picture of it this time. You actually develop. So if you put it through a prism, this is at the bottom, a lamp, sort of like the ones up here. Although I think it's filled with neon. This one, I actually don't know off the top of my head. I'm sorry. Anyways, basically, when you split it with a prism, you get these individual lines, which you see off to the side. If you heat up, like say a metal, or even a liquid like water, really, although it would be more difficult to see because the spectrum wouldn't be in the visible. But if you heat up something as easy as an incandescent bulb, they don't even make incandescent bulbs anymore, right? But when I was a kid, all the light bulbs were incandescent. It's basically just a hot metal filament, right? You drive a current through it, it gets all frictiony and hot. Well, if you split that light, you get this really beautiful rainbow. Now, what we see coming off of the surface of the sun is more close to that rainbow thing, right? And so this is the main point that I was trying to impress upon you. Now, it's a little bit more complicated than that because the sun has an atmosphere that is absolutely gaseous, just like the Earth has an atmosphere that's gaseous. We probably don't think about it, but this room's full of gas right now, quite a bit of it, actually. It's actually at an extraordinary pressure. There's pounds of pressure pushing on all sides of you right now. The reason you don't feel it is because it's pushing from the inside out too. You were formed in the same environment. There's a lot of gas in this room, and there's a lot of gas in the atmosphere of the sun. And so we do see little lines on the sun, and we'll talk about those in the solar atmosphere. But there's something really pernicious about this beautiful black body spectrum, this rainbow, this continuous radiation that we see from the sun, which is really reshaping our understanding of the sun in this moment. And this is an absolutely critical point. And if it's not clear to you why that matters, it will become unbelievably clear, because every single piece of the puzzle that we're going to wander into when it talks about, when we start talking about the formation of stars, the fate of stars, right? We're going to be talking about this idea about black holes at some point, right? Which everybody loves to talk about. Many of the theories that we find that we've inherited to this day depend on this gaseous sun in order to produce those phenomena that we've landed on. And so if the sun is not a gas, then we will have to look for other theories. And so it turns out to be quite important. And of course, there's a technological arm to it too. Thoughts? Give me some thoughts or any other, what else? Yeah, David.
That was interesting when you said that they've kind of been making claims that they've been getting closer to like producing fusion power, but in reality, it's they keep trying to like shrink it down or like whatever machine that they use to do it, but it's probably never going to happen in reality.
Yeah, that's something which really bothered me when this is all coming out. There's a video from Neil deGrasse Tyson that was going around where he was claiming, you know, all these gains from this latest reaction. And it's really unfortunate because you actually have to have some technical knowledge to read the white paper and see that like this is actually not the case at all. In fact, it's so not the case that it was hundreds of times the amount of energy required to actually power this reaction in the first place. You know, I think that what do I want to say about that exactly? I mean, I think that first of all, being a professional scientist is really tough. You know, there's a lot better ways to make money in this world. Like you go into, like almost everybody I know from the physics department at Columbia, where I did my PhD, went into finance or something like that afterwards, right? Because you use math and you do the same thing, but you make a heck of a lot more money than being a scientist. Scientists are fighting over breadcrumbs when it comes to actually getting money to do the experiments they want to do. It's very difficult to get money in science. So I think that there's something we have to always watch out for, which is that people always want their results to look cooler than they are. Which is unfortunate, but it's also driven by the economic climate of trying to do that work. And so, you know, I'm sure that they've improved their plasma fusion reactions a little bit, but telling, you know, a funding committee that you've improved it a little bit is not such a surefire way. And so every few years we'll see these headlines about these enormous gains in fusion research, and yeah, they're unfortunately misleading. So yeah, I don't know. There are some promising approaches, though, and I think we'll be seeing more of that as we come to understand the sun better, ultimately. What else? That was a good point. Thoughts?
You
Can-
began to get at the lattice confinement.
Yes.
Talk about that.
Yeah. You know, I should drop a paper in about that. Problem with scientific papers is that they're so impenetrable. They're just riddled with jargon and so forth. The basic idea, though, there's an alternative approach to fusion, which really just involves taking a metal and essentially soaking it with all the same atoms that you would have in this gaseous version of these giant magnetic fusion reactors. And then you can, you know, just at room temperature, you can apply the same kind of laser pulse that you would to the gas. And you can squish those guys in the little pockets between the lattice. So this might be a good opportunity to talk about lattices in general. One of the reasons that it really, really matters what the material structure of the sun is that depending on the properties of a lattice, so all a lattice is it's kind of like, it's like a cage of atoms, right? The atom generally exists in a material, like say this table, in some sort of a cage, like a three-dimensional structure where they're bonded together. And, you know, this is going to be in 3 dimensions. And it might not be this perfect crystal that I'm drawing for you right now, but in some sense, there is a repetitive arrangement inside of all solid and transient lattices occur inside of liquids. So the interesting thing about this is that gases, unlike solids and liquids, do not have lattices, actually. It's completely chaotic and random. So there's really nothing to remark upon. If you believe that a substance like the sun is made out of a gas, then you don't have to concern yourself with the lattice. Now, why does that matter? Well, here's a good reason why it matters. Because depending on the shape of this crystal or this arrangement, you get wildly different optical properties. I always like to use the example of carbon. So you guys know about carbon crystals, right? Anybody have one on their finger right now? A wedding ring or something like that? Anybody married? Yeah, so, or engagement rings usually are carbon crystals. They're diamonds, right? So diamonds are made out of carbon, 100% made out of carbon. But you know what else is made out of carbon? Soot, right? How about basically like graphite in your pencil, right? Now, soot and graphite don't look anything like diamonds, right? But they're both 100% made out of carbon. So what's the difference? The difference is that inside of soot, by the way, all of the experimental black body chambers, when they were originally trying to figure out this stuff, they covered them in soot because black means it absorbs all the light. So the black bodies were made out of soot-covered containers, essentially, because they absorb all that light. So the crystal structure of soot is it's a hexagon, right? The crystal of a diamond is very different. It's actually a three-dimensional shape, but it looks a little bit like a cubic crystal of some sort. It has it has a tetrahedral structure to it, let's say. So just the difference, just by literally putting the atoms in different places in the solid, by having a different repetitive crystal arrangement of them, you either get a completely translucent black object, right? Like carbon, soot, or you get a completely transparent object like a diamond, right? So you guys can start to see how considering the lattice structure of a material is going to wildly change how that object looks. So for instance, if I'm looking at a star, and it's, well, this requires some preamble, but if I'm looking at a star that's really far away and I'm trying to understand how far away that star is. Have you guys ever been like out on a road at night and you see like a headlight coming to you, right? And you think, well, that thing seems like it's really far away. And then all of a sudden you realize it's like a bicycle or something, and it's very close to you, actually, it turns out, right? It's a little tiny headlamp, right? So this is kind of what we do in astronomy, is we try to look at how bright something is and say how far away it is. And I'll break down to you with luxury of detail how that actually works out. It's a bit more complex than that. But if you have something that has a lattice structure that isn't very optically active, like a diamond, for instance, right? And you have one at the same distance that is very optically active, like a carbon, for instance, like a soot, right? Same stuff, but in totally different lattice arrangements. Well, that diamond object is going to be really, really dim, right? Light's going to sort of pass right through it, right? It's not going to glow in the same way. And so the same thing, we need to start to really, this is really cutting edge as far as how people are thinking about stars, but it's a very similar situation where if we've been for the last 100 years neglecting the actual material arrangement of the star structures themselves because we say, they're gases, they don't have structure to them. Well, we might be making some really egregious mistakes when it comes to trying to say what that light from that distant star actually means. It might be the bicycle instead of the semi-truck that's really far away, for instance, something like that. This will all make sense in due time. So, okay. What else? Thoughts, concerns, questions? Yes, tell me your name. Yes, Kai.
So does that tie into the metallic hydrogen?
It does indeed. So liquid metallic hydrogen, phenomenally enough, nobody actually knows, like there's determining like the structure of it is very difficult. And there turns out to be different proposals for the structure, but one of them is actually very similar to this hexagonal planar structure that we get from soot. And I think it's a reasonable proposal because if we are dealing with something like that in the sun, we should expect that this molecule or this lattice arrangement that gave us all of our early experimental data on black bodies would be recapitulated because the sun is one of the most perfect black bodies that we've ever seen in nature. I can't think of a more perfect black body. Most objects, like let's say if I was to heat up this table or something like that, it doesn't have, it's black, but it's also, I can see it's got some specular aspects to it. It reflects some light as well, let's put it that way. So we would say that its emissivity is not quite perfect, right? So it's not going to give us a perfect black body temperature as a result of it, though it's heated. It's going to be somewhat off, right? soot-covered chambers like this actually give us very close to an appropriate temperature. In other words, you can measure the light from it. I think we'll talk about how the equation that you use for that, but it's kind of unimportant. What's important is that you can judge the temperature by how that peak of the blackbody curve shifts. Liquid metallic hydrogen can also do the exact same thing. It's an interesting proposal. And the sun is made out of hydrogen. That's not in dispute at all. There's a bunch, basically everything in the world is inside of the sun, but most of it is hydrogen. The next biggest piece is helium. And then there's a bunch of other trace elements and so forth. So yeah, it's an interesting proposal. I actually just uploaded a paper. If you guys are interested in more of this theory, I just uploaded a paper to your Moodle. My a close friend and colleague of mine who wrote a sort of he gets into all the details, let's put it that way. So it's an interesting proposal. Thoughts? This is a good question. All right. Let's keep cruising with our tour then, in that case, of the different layers of the sun. Keep bearing all of this in mind. I guess we'll have more time to talk about the details of light itself. But light I'm not sure how deep I want to get into light right this second. Light is a really bizarre situation because it's something that we have incredible knowledge of how light behaves and how it scatters and how different bodies and gases emit it and all the characteristics of this, but it's also very poorly understood exactly what light is. Is it just this piece of magic that's thrown off of one atom and caught by another one? It's often portrayed that way. But, you know, one way that I would urge you to start thinking about light, which I think is a bit more appropriate, and I think I can use this to explain to you why gases and solid bodies have very different light properties, is that light never happens without two atoms, at least. So, you know, the easiest test of this is that you have an eyeball and there's a light source above the room. And so at least every single light transaction that's ever been experienced or witnessed or observed, all the light we ever know about, at least involves an emitter and absorber. And what's really interesting is if we were to bore ourselves with the quantum mechanics of the situation, what we would find is that the first atom that's emitting the light is in some state of heightened motion, right? So it's vibrating is probably a good way of thinking about it. We would say that has an energy state of some energy state. The atom that absorbs the lights at the other end of the transaction, it takes that exact same amount of energy, that same level of vibration upon itself. So light is really this interesting equalizing process by which two atoms are able to essentially take all this extra freneticism and transfer it to its neighbor, right? And so what's interesting is that in a gas, right? Gases aren't really directly held in place by anybody. They're all on their own. Gas is sort of like a bunch of atoms that are all just loners at a party, right? Now, what's interesting is that if you're not connected to anybody as an atom, you really, and atoms can more or less be approximated as spheres, right? They all have, there's more details to that, but we can essentially think of them as spheres. A sphere can only really vibrate in a few different ways, right? It can kind of go up and down, it can go to the side. It really has we would say it has limited degrees of freedom from which it can actually deform itself. But what happens if I take 2 spheres, 3 spheres, 100 spheres, and I link them all together inside of some sort of lattice, right? Now all of a sudden, I can vibrate with my neighbor to some extent. And actually, in these substances, particularly in metals and so forth, and in these carbon structures that we're talking about with blackbodies, they really start to share their outer surface. We would say that their electrons become delocalized. What that really means is that these atoms, where one begins and the next one ends, is almost indistinguishable. And so something really interesting happens at that point. You have all these new vibratory modes that appear, right? You can vibrate with your neighbors, you can vibrate by yourself. there's basically a geometrically multiplying number of possibilities by which you can vibrate. And that's why you get this nice continuous spectrum out of solids, liquids, versus out of gases, where they can only really vibrate in a few ways, because they're just individual atoms. So we'll keep coming back to light, but I think it's important that you start thinking about it as a transaction between an emitter and an absorber. All right, now most of the light, well, I would say, yeah, most of the light, 99% of the light that we see from the sun comes from this layer of the sun that we call the photosphere. And this is a picture of the photosphere. Now, what's really interesting is that, you know, when you're talking to people, solar physicists and so forth, they would say this photosphere is the surface of the sun. And I think that's a totally reasonable way of thinking about it, because above this photosphere, we just sort of have this diffuse gaseous atmosphere. It's quite evident. They'll also tell you there is no surface to the sun, because, of course, a gas can't really have a surface to it. Now, that's a bit perplexing, because actually, as you look at the density of the atoms in the atmosphere of the sun versus down in the photosphere, as it reaches the photosphere, the density of those atoms starts to approach that of water itself. Now, what happens when you compress a gas, generally speaking? You guys played with like dusters. Anybody scuba dive? What happens to a gas when you squish it? Yeah? What else? Yeah, I mean, have you seen like these oxygen tanks? Are they full of gas? It turns into a liquid, basically, right? Because the atoms can't move anymore. They're stuck with their neighbors, basically, right? And so it's essentially all those atoms are in contact with one another constantly. And so you reach this really interesting point. And as we go down into the depths of the sun, we find that density increases from 1 gram per cubic centimeter. That's like water, to like 20 grams in the outer layers. And then at the core, it's like hundreds of grams maybe thousands of grams per cubic centimeter. And so again, you really have to stretch the imagination to call something that's at 20 grams per cubic centimeter a gas anymore. It's very much an extremely dense liquid-like substance, whatever it is. Problem is, of course, then we have to start considering the material properties of it, which could change the whole story. Okay, so the photospheres, this is another really interesting mystery about the sun. The photosphere is hot, but it's not that hot. So the photosphere is at about 5,800 Kelvin. I mean, it's hot enough it would burn your hand really badly. But the weird thing is that when astronomers try to construct the temperature of the outer part, the corona, the atmosphere of the sun. Has anybody seen an eclipse before? Yeah, cool. Oh, wow, awesome. You see it this year?
The partial one?
Okay. Yeah. Did you see the corona? The little gaseous pieces wiggling around? Anybody see that? Yeah, I saw it this last year too. I went down to Texas. It was pretty awesome. Yeah, so you can actually see this corona, which is the outer sort of the ray-like parts of the sun, The funny thing is that when scientists try to reconstruct the temperature of the corona, they come up with something like 2 million degrees Kelvin. Now, to say that the surface of the sun is at 5,800 Kelvin and the corona is at 2 million Kelvin, well, that's a really interesting situation. That's kind of like saying that you have an oven whose walls are like 2 degrees and you have the gas inside it, the air inside of the oven is at 1 million degrees, right? This kind of boggles the mind. And so, this is actually, I'm not sure how your textbook says this, but it's essentially a huge outstanding mystery about the sun. How in the world does it go from having this really cold surface to having this extraordinarily hot atmosphere? Now, they have recently, there's been a NASA mission to visit the corona. It's called the Parker Solar Probe. Anybody read about this thing? Heard about it? All right, well, I had a chance to talk to this lady who was the head of the program on my podcast a couple years ago. And I was like really pressing her about this because they send a probe into the corona. They literally send a spaceship into the corona, and they're measuring temperatures in the millions of degrees. And I'm like, I started asking her about this. I'm like, can a spacecraft really withstand millions of degrees? Well, not really. No, the heat shields are actually only tolerant to like 3,000 Kelvin, let's say, or 2,500 Kelvin or something like that. Well, how in the world does that work? Here's where things start to get really weird, is that temperature, does anybody remember the definition of temperature from like intro chemistry or something like that? Come on, somebody. What is temperature? Anybody?
Like,
Yeah, shout it out. What is it? Okay, Adam's moving. All right, that's good. Yeah, temperature is the average kinetic energy of a system, which is just science speak for how fast stuff is moving around, right? The funny thing about average kinetic energy is that if you have only one atom in this room and it is moving at some appreciable speed, like fraction of the speed of light, the average temperature of this room is going to be gazillions of degrees Kelvin. Now, does that mean that this room is going to be very hot? No, it's going to be freezing cold because there's only one atom in it moving around, right? So the concept of temperature starts to really fall apart when you have a really low density substance like the atmosphere of the sun, the corona, right? So this temperature thing is, the concept of temperature that we're used to is really not quite the right way to be looking about what's going on in the corona. And there's other issues associated with that as well, but I think that's probably the main reason why this seems like such a confusing situation to people. Okay, so, probably about time that I showed you guys the Blackbody curve for the sun. This is essentially the Blackbody curve that we measure from the photosphere, which is the surface of the sun. What's interesting is that you can see that as the temperature gets colder, so these are all Blackbody curves, you see that the peak of the curve moves slightly closer into the red and away from the blue. So when we look up at the sky and we see a blue star, the first thing that we think is that it's shifted to the blue side of things, and it's really, really hot, right? So you've had this experience when you look at a fire or something, right? The glowing, really hottest part of the fire tends to be the bluer side of things, right? And of course, this extends all the way out into the infrared and presumably even out into the radio wave spectrum of light. So when I say light, by the way, guys, I always forget that I have to clarify this. When I say light, I don't just mean like visible light, right? I mean all electromagnetic radiation. So the stuff coming out of your cell phones is light too, right? X-rays that you might get at the doctor or at the dentist, those are light too. They just happen to be extremely blue light, really, really, really high energy. Blue, it doesn't have a real color to it, but if it did, it would be blue. And cell phone radiation and so forth would be red because it's really long. So this is kind of how we start to make understandings about the temperature of the stars that we're looking at. Now, the annoying part about this, of course, which I have to just keep reminding us, is that it might not be quite as simple as that because, of course, this estimation of temperature, which is quite reasonable if you have a perfect black body, right? Same as the one we study in the laboratory. It starts to fall apart very quickly if the lattice structure of the body you're measuring is not perfect, right? Or if there's reflective aspects to it, like this desk, or, like I said, if the lattice is more like a diamond than a piece of soot, then you're going to measure a very, very incorrect temperature from the surface of it by looking at the color. It's just not going to be even close to right. So it's tricky. If you can grasp this, then you can grasp 99% of the primary data that goes into the stories that we're telling about the stars, because all that we have is light, right? We have different flavors of light. We have the really high energy light, and we have the really low energy light, right? We have gamma ray we have X-ray telescopes. We can see gamma ray telescopes. We can see radio wave, infrared. We can see all these different colors, for lack of a better word, all these different frequencies or wavelengths of light. But we have to interpret that light at the end of the day, and we have to say, what do we think it means? Why is that body giving off that light? Cool. Questions? thoughts, worries? Is anybody worried? I hope not. Okay. All right. So what does this actually look like when we actually look at the sun? This is what it actually looks like. This is kind of cool. So if you took a prism and you split the light from the sun, what you would see is you would see a beautiful rainbow, but you also see these black lines over top of it. What are those? Which part? Which part of the sun do those tell us about? What about the black parts in particular? So there's a nice bright spectrum behind, and then there's these little black lines over top of it. Here, yeah. Yeah, why are they missing?
Maybe we just can't see them.
We can't see them. Why can't we see them? Yes. It is. It is. What else? Come on. Somebody's got this. Which wavelengths? So remember, gases give us lines, right? Gases give us lines. The piece of the puzzle, yes.
Blocked by that.
That's exactly right. They're being blocked by the sun's atmosphere, actually. So here's the piece of the puzzle that I didn't tell you guys. If something is something is emitting light at a certain frequency, any atom, whether it's a solid, liquid, gas, doesn't matter. If it can give off that color of light, it can also absorb that same color of light. And so what we're seeing is the photosphere giving us this beautiful rainbow, right? The body of the sun giving us this beautiful rainbow of light. And the atmosphere of the sun, different types of atoms that are soaking up individual frequencies across that, right? So these are actually absorption lines. They're individual frequencies. They're individual colors that specific types of atoms are grabbing up and screening away, so that when we look at it across the prism, we see not only the surface of the sun, but we see the atmosphere and all of the different atoms that are in the atmosphere that are absorbing. Does it make sense? All right. So here's another way of looking at that. Each one of these gases can absorb a few different colors usually. So you see, if we break this down a little bit more, we see some of the more dominant lines that we find in this atmosphere. Obviously, hydrogen, most of the sun is hydrogen anyways. Some of it is gaseous in the atmosphere. It's absorbing those colors. Calcium, mercury, sodium, just about everything that you can think of is found in trace amounts in the solar atmosphere, which is really, really interesting. Okay. So this is nice because whenever when we start to look at other stars besides our own, we start to be able to understand a little bit of differences between each of them in terms of their composition. So not only do we have access to the temperature of the sun through the blackbody spectrum, assuming that it's an ideal blackbody, but we also have access to questions about how metallic is it, right? Because we're going to see how strong the different lines are. We can actually make assertions about what that solar system is like. Does it have a lot of calcium? Does it have a lot of mercury? These might seem like pointless questions to ask, but they're really interesting to us on a lot of different levels. They tell us about whether perhaps that's an interesting solar system for us to train our eyes on. As I think a lot of astronomy these days is honestly based on trying to find another place for humans to go and chill out at eventually, because we need a backup hard drive for this place. So there's a lot of people who are really interested in what's a habitable solar system look like. And part of that is trying to understand what the chemical composition of those solar systems are, which relates back to its star. So we get a lot of information about that. This same phenomenon plays out in the atmosphere of planets too. So when we're looking at these exoplanets, planets in other solar systems, and we're trying to say, is that on Earth-like or is it not? Well, we're looking for obvious things that we need, like oxygen, right, and water, which are going to give us the gaseous forms of oxygen and water are going to have specific lines, fingerprints that we can see as that star's light shines through the atmosphere of those exoplanets. But it's also going to tell us if there's like poisonous cyanide in the atmosphere too. And we probably want to avoid that, right? So we get a lot of information. This is kind of like the fingerprinting of an atmosphere. Yes, please.
Those same wavelengths.
Our solar atmosphere.
Okay,
Yes.
yeah, as I was like, wait a minute.
Although that's an interesting point though too. Our atmosphere, of course, absorbs. It's full of gas, and it does absorb. It does absorb quite a bit. What's really interesting, though, if you look at our atmosphere, is that it has a few optical windows in it, right? And those optical windows, it absorbs all sorts of light. And thank God that it does, because if it didn't absorb X-rays and ultraviolet radiation and so forth, we would all have our DNA shaken apart, essentially, right? But there's this really coincidental, beautiful little window in the visible spectrum, just in the colors that we're all accustomed to in our daily lives, where that light passes right through. Now, oftentimes, neutral gases, right, non-ionized neutral gases, like do you guys know what most of our atmosphere is made out of? This is always fun. Anyway, nope. Nitrogen. 80% of our atmosphere is nitrogen. How much is oxygen? It's almost 20%, actually. Yeah, I should have led this backwards. I love asking people what percentage of our atmosphere is carbon dioxide. I always get like 60% and stuff. It's like 0.04%. Okay, so we have this beautiful window, actually, where visible light. Do you know where the other window, what other kind of light makes it down from up top? Anybody? It's kind of interesting too. Yeah? No? Yeah?
Radio wave.
That's right. Yes. Radio waves. We have another window in our atmosphere where there's no radio waves being absorbed. And so if you go out, we talked about, we had more time for this last semester, but one of the types of telescopes that we use in astronomy all the time are these enormous arrays of radio telescopes. And you'll see them often parked out in the desert because radio waves can be absorbed by water, so clouds can get in the way for sure. But yeah, we can have really nice telescopes that observe in the radio wavelengths. That's really, really useful. So yeah, we have these two really nice windows on Earth. Otherwise, everything else gets screened out, and it's a really good thing. It probably, I like to, it's like, why do we see in the visible spectrum that we see in? It's like, well, what's up?
How are like these layers compared to like the other atmospheres and like the stars? Like how is it like the same thing, or is every star different?
They are all different, and they're all very much the same too. There's classes of stars. We'll work our way towards that. It's also there's a lot of uncertainty in that too, because we're doing the best we can in terms of classifying those, and I'll get into all that. But they're basically classified in terms of temperature and the atmosphere. So what lines we get out of the atmospheres of them, and we'll talk a little bit about the ways they're grouped. Where's I at with this atmosphere thing? I guess I didn't really mean to talk too much about Earth's atmosphere, but I do want to point out it's really interesting that our eyeballs seem to have evolved or adapted to work under the only kind of light other than radio waves that makes it down, that isn't screened out by our own atmosphere. And to my knowledge, there's no animals that see radio waves, but maybe there are. I don't know. I wonder if it's just something we haven't. There are animals who can navigate based on magnetic fields, right? I think some birds do this in a really interesting and poorly understood way. So maybe there's something to that. Maybe there is some actual radio perception. But it is interesting that nobody evolved to see in radio waves, from as far as we know, anyways. All right, so let's talk a little bit about the standard model of the sun and its layered organization. I suppose you guys can read mostly about this in your textbook. The thing is enormous. It's by weight, or let's say by mass. And I hate to do this without explaining mass, but it's gravity, right? The amount of atoms it has all pulling on one another. is something like more than 300,000 Earths all crammed together, right? It's an enormous, enormous beast at the center of our solar system. All right, we talked about the atmosphere, the corona a bit. There's something quite interesting. So the surface of the sun is constantly off-gassing. So what is that? It's kind of like, you guys ever play with dry ice or something like that before? Right? You ever notice, like, if you take dry ice and you basically put it in an ambient temperature, all of a sudden, it goes straight from a solid substance straight into a gaseous form, right? Surface of the sun is doing something really similar to that. It's called the solar wind. And the solar wind is, it's both being held in place by the gravity of the sun, and it's also being held in place by the magnetic nature of the sun. So we need to talk a little bit about how magnets work before we can make sense of how the heck that works. But for now, let's assume that there's a lot of particles that are sublimating and flying off the surface of the sun. These are essentially hydrogens that have been ionized. So from an accounting perspective, they're ripped into their constituent protons and electrons. I don't think that's quite the right way of thinking about it, but they are in some sort of excited state as they're flying off. This predominantly happens from the equators of the sun. So if we were actually to look out and zoom out from the sun, we would see something like a ballerina skirt of this material as it's spraying out on all sides. Of course, the sun is rotating. It's turning. It's actually turning faster at its equator than anywhere else, which is quite interesting. And the details of this very beautiful structure of particles that are flying out of the sun it's a really, really brand new topic of study. And we call this thing the heliosphere. So once it reaches the far edges of the solar system, it actually kind of folds back on itself and forms this really interesting bubble. This is kind of like the best picture I could find of it. But this bubble, which is in some sense insulating us from the rest of the universe, is crashing up against the interstellar medium. We'll talk about what that is later. But there's a bunch of stuff out beyond our solar system that we're crashing into. And there's actually a kind of sonic boom because the solar system is flying through the galaxy. Remember, not only is the Earth orbiting the sun, but the sun is orbiting the center of the galaxy. And it's moving at quite a click, actually. Right? So there's actually this sonic shockwave of this heliosphere as it crashes into it. If you guys are interested in that, I talked to a really interesting dude at Princeton a couple of years ago named Eric Zernstein, who's studying this. It's very poorly understood how the star systems actually interact with one another, right? So do we ever brush up against our neighbors, right? That's an interesting question with respect to the solar system. We do know that the edge of our solar system essentially reaches halfway to the next star, right? So if the next star has a helios sheath of this material that's kind of a bubble enshrouding it, then presumably the different star systems are actually like little bubbles that are essentially in contact with one another, right? Now, we'll get into this in much more depth later, but one of the biggest problems in all of astrophysics right now is the problem of why the galaxy doesn't seem to move like a solar system. So in our solar system, all of the interior planets are being pulled on the sun really hard. The gravity of the sun's pulling on them, and they're spinning really fast. So Mercury is really whipping around the sun really fast. But Pluto takes, years and years and years to make its way around the sun, right? The galaxy is not like that, though, and it's really confusing, really, really confusing the heck out of astronomers right now. So the galaxy seems to move as one big unit, more or less. It just turns like a giant disk. It doesn't move in this kind of vorticular way where the interior stuff goes around really, really fast. It does to some extent, but it's not nearly as much as it should if gravity were at play. And so, the astronomers have actually plugged the hole in their equations with this stuff they call dark matter because they don't really know what to make of this. It's not actually behaving the way that it should. And so the interesting dynamics of helios sheaths and this frictional interplay between different solar systems is a kind of cool lead that could actually lead to some interesting answers about that. All right, so the sun. you know, one of the things, the best thing that we have when we look at the sun is like, we can actually see the surface of the sun, the photosphere. One of the things we see when we look at the photosphere is these little kernels, right? Kind of looks like, I don't know, like corn or something. It turns out that we can explain these, this kind of kernel stuff, which we call granulation on the surface of the sun, in terms of convection. So you guys ever, how do I explain this? You ever been like boiling water, or you're making some noodles or something on the stove, and you see these little patterns of boiling come up, and maybe you get like 3 of them or 4 of them inside of a pot, and you see these stable little like bubble systems. Anybody seen this? Know what I'm talking about? A little bit? Check it out next time that you're cooking some mac and cheese or whatever the heck you guys do. You'll actually see these stable cells, and what those are is that as the water is heating up, as it gets heated up, remember, temperature is just motion, right? So the water molecules that are moving really fast, they take up more space. And so just by gravity alone, since they occupy more space, they're less dense, they rise to the surface. And so you get this really interesting cycle of rising, and then it cools and falls back down. You get these bubbling circles, and you actually get static, almost stable structures. Now, in liquids, these are called Banard cells, but it doesn't really matter. The point is, the same thing's happening on the sun. At least that's to the best of our ability what we interpret this kerneling structure to mean, is that each one of these granules, by the way, I want to say these granules are like the size, on the order of the size of a planet, right? They're huge. They're huge Banard cells, essentially. But these are, and this is kind of a good picture. These little rings that you see are those little convection cells as they bubble up, and we just see the tip of them at the photosphere where this is all going down. Now, you also see on the photosphere, depending on what place in the decade we're at, because there's a 10-year cycle we'll talk about. See these little holes, right? These are called sunspots. You guys heard of these? Anybody ever seen a sunspot before? I had something really crazy happen a couple of years ago where it was like during one of those really bad fire summers, and the sun, when the sky's all smoky, you can actually like look right at the sun sometimes. It was like pink behind this cloud of smog and smoke. And I was looking at it, and I saw this little black dot on it, and I was like, oh my God, is that like Venus going in front of the sun or something? So I like went and looked it up, and no, it was just a sunspot, it turned out, actually. And I could just see it with my bare eyes, no telescope, nothing. Now, do not look at the sun through a telescope. Had many disasters doing such a thing. But you can see it very nicely if you project it onto a wall as well. But you can see it when it's behind a cloud or something. You can actually see sunspots. So if you have the opportunity, the sun's behind a cloud, you're not going to burn your eyes out. Check it out. And depending on what year it is, there will be more or less of these things. So sunspots are really, really weird and mysterious, and they're another piece of the puzzle that we need to try to make sense of. Sunspots, at least according to your textbook, the sunspots are cooler. I think that's a reasonable thing to assert. Why do they think they're cooler? They're darker. Yeah, they have less light coming out of them. Now, unfortunately, we all know in this room all of a sudden that there's other reason for things to be dark besides the fact that they're cold. So jury's still out on that one. However, they do, some of the earliest arguments about sunspots was that they did seem to portray an opening in the sun by which you could see down to a different depth inside of them. The sunspots are also, if you look at a sunspot from the side, I just had some white chalk. I know. Oh, here we go. If we look at a sunspot like at the limb of the sun, we often associate these really beautiful projections of this magmatic stuff from the surface. So this is like a side view of the sun. This isn't supposed to be the North Pole or anything, but this is our sunspot. You actually see these beautiful loops of solar material around them, right? So we know that sunspots, and this is, of course, organized magnetically. And I'll explain to you how magnetism works, and hopefully before the end of the day here. So we know that there's some sort of a magnetic null spot inside of these things, and the standard explanation is that because this magnetic structure is actually able to nullify the convective ability of this kerneling. So in other words, it prevents this convection from happening as efficiently inside of the sunspots. Therefore, there's less heat, let's say, rising, and they're cooler as a result of it. I have my reservations about this, but needless to say, there's some obvious magnetic structures that are happening around these things. Let's see if we can, well, let's go through a few more little pieces. There's also these really beautiful things called spicules that rise up from, this isn't a great picture of them, or it doesn't reproduce perfectly, but they look like these little, almost hairs that rise off of the photosphere up into the atmosphere. Here's a better picture of them from the side that's been filtered a little bit more. Spicules are really, really weird because they actually, they seem to be a continued piece of the actual surface of the sun. They seem to have that same black body spectrum to them, right? They're not gaseous, they're not like tornadoes or something like that. They actually seem to have some substance to them, which is really quite interesting. Okay, we've talked about the corona. All right, we do need to talk about the solar cycle, and we need to talk about these sunspots. So, sunspots are weird. One thing that's worth noting here is that people very early on, people have been tracking sunspots forever. People were making note of them long before they had telescopes, and I don't know how they were pulling that off. But people started to keep really good records of them at the dawn of the telescope era. By the way, when did the telescope appear in the universe? At least in our universe. Anybody know? Who was the first person to point us? Well, who invented the telescope?
Yeah.
Galileo was the first person to point it at something other than a ship. Yeah. So it was actually these Dutch like eyeglass manufacturers just had this brilliant idea that they put the two eyeglasses in front of each other. They could focus the light, and they were sold as nautical instruments originally. But Galileo, right, in the 1600s, decided that, hey, what if I point this thing at the sky? And so he solved like 100 different mysteries in astronomy and astrophysics overnight, essentially, as soon as he did that. But anyway, when the telescope became super mainstream after Galileo, people started keeping track of these. And what they noticed was that there was a very obvious cycle by which, every decade, essentially, you would go through this period where there would be a lot of sunspots, and then they would disappear over the course of the decade. And then they would reappear over the course of the next decade, right? This is still really, really mysterious to scientists exactly why in the heck this happens. But what we do know at this point is that as those sunspots appear and reappear, that the magnetic polarity of the sun changes each time too. So north pole of the sun becomes the south pole every 10 years, which is pretty crazy. To give you guys some context, we have a north pole, a magnetic north pole. That's why your compasses work and stuff like that on Earth, right? Here on Earth, we have a magnetic north pole. Our magnetic north pole also changes and becomes the south pole, but it takes like 1 million years for that to happen, right? And it is actually, we are due for one, just to be quite clear about that. Should be totally fine, but we will go through a polar reversal at some points, in the next few thousand years, it seems like. The sun, it happens all the time, every 10 years, like clockwork. And I want to, maybe next class we'll start to get into how that affects things on Earth, but we think that it really does affect things, including the climate and the weather here on Earth, which is quite interesting. So, yes, exactly. How about we try to understand what the pole of a magnet is first? If we understand what a magnet is, then we might be able to talk about how poles reverse. So let's do this. We have 10 minutes left. Let's talk about what a magnet is, and then we'll start right there at the next class, because that's where things start to get really, really interesting. If I wanted to make a magnet, there's a really simple way I could do this. And most of the magnets, magnets that are in your phone, in this receiver that I'm using to record this with, let's say 99% of the magnets we use on Earth are of the variety of an electromagnet, right? And this is essentially the kind of magnet that we find in the sun as well. So how the heck does that work? I think that, and I apologize, I know there's a couple of you guys who were here last semester, so this will be a review for you. I want to give you a way of thinking about electromagnets, which is a way of visualizing what the heck those atoms are doing inside of it so that it's not completely magic to you. I think that this is a simplification, but it is a very useful way of thinking about it. So there's something really bizarre about atoms in general, right? When you studied intro chemistry in high school or something like that, you basically got this model, I've pointed it out before, where there's like a nucleus of some sort. This is a very simple atom. It's a hydrogen. It just has one proton. It has one electron out here, right? This is like some sort of schematic, right? Now, maybe you took some more advanced chemistry classes and you learned that the atom is actually more of this undulating sphere, right? And the electron is kind of everywhere all at once and nowhere, right? But again, it's probably represented, you represent a hydrogen as a sphere of some sort, right? Okay. Now, the thing that escapes most, high school and college level textbooks about until you get into quantum physics is that this isn't exactly accurate. The outer surface of the atom is the electron, right? But what's really funny about the outer surface of the atom is that if we draw, let's say the probability of finding the electron on the y-axis, and we draw the distance away from the nucleus over here, right? What's really interesting is that we don't find the electron at the nucleus. It can't be where the nucleus is for whatever reason, but it does appear, we find it almost always right at this shell, the outer surface of the atom. But what's really, really crazy is that this curve actually goes off to infinity. That means that the surface of the atom actually, in some rarefied sense, can be found at any distance from the nucleus. So the outer surface of the atom seems to have a shell-like component, and it seems to have this kind of hairy, amorphous region way beyond the shell, by which it can actually presumably interact with its neighbors, right? So when we start thinking about magnets, it's easy to just start with a simple atom, right? The atom, just like a regular magnet, can be treated as a little magnet. And it has an electric orientation to it. It has an electric north and south to it, just like a wire, right? It has the direction in which the current travels. And naturally, the magnetic component wraps around its equator like this. So this would be the electric component. This would be its magnetic component. Now, what's really interesting is that if we make a wire out of these atoms, so if I could make a single atom wire for you really quickly, it would be a bunch of, there's no such thing as a single atom wire, but if there were, it would be essentially a many atom wire would work the same way. What happens is if we drive a current through this wire like this, then the outer surface of the atom can be thought of as rotating orthogonal to it like this, around, right? It's curling around it like this. You got to keep in mind, like I showed you earlier, that the outer surface of the atom does extend indefinitely. So not only is the surface, the shell of the atom rotating, but it's also reaching out in all directions around it in every single way. And so if I put a wire like this next to another wire like this, where the current's going in the same direction, those little pieces of the atom are gripping onto each other. They're interacting and they're meshing, and these wires will actually be drawn to each other. This is the most simple form of electromagnet. It's two wires that are running with the current in the same direction. They actually experience a slight magnetic attraction to each other as those atoms are kind of pulling each other towards one another. If we run it in the opposite direction, then those surfaces are pushing against one another, and you actually get a repulsive effect. Now, what happens if I take that wire and I curl it up like this? Well, if I do that, what I find with all these little atoms is that their equators, all of the equators of the atoms are now lined up perfectly, such that we can think of their magnetic moment of each atom going into the board like this. See? These are arrows going into the board like that. What happens is that they all synergize. And this coil now, having all of its equators lined up, has a single magnetic field that results from it. The coil actually amplifies the behavior of each individual atom in that wire now that we've put them equator on equator on equator. Okay, this same thing is happening under our feet in the magma below us. As the Earth turns, all of that magma is getting forced to swirl about. It's called a Coriolis force. And this is also really conductive material. So there's actual little, these solenoids, right? That's a simple coil of electric wire, essentially, is happening naturally under our feet. The same thing is happening in the sun. Now, when it comes to understanding these reversals of the pole, we have to start thinking about the core. So does anybody know what I'm missing from this depiction of an electromagnet? Let's say I want to make an electromagnet to lift a car in like a dump or something like that. What am I missing? Anybody? A big piece of iron, right? So electromagnets, when we stick a big piece of iron in the center of this coil, it amplifies the iron. Have you guys ever magnetized paper clips before or something like that? Iron can be imprinted. Its lattice is, in some sense, allows the atoms to rotate in line with an existing magnetic pressure that's being applied to them. So iron can get, and other metals can do this as well, but iron's a great example because iron can actually amplify by being imprinted with the magnetic coiling structure, can actually amplify the field and stabilize it too. So there's some thought, particularly with respect to our own core structure on the Earth, that what's happening when we have a pole reversal is that imprinted iron core is actually tumbling in some sense when that pole reversal happens. So I'm going to relate that back to the sun, but it's too big of a story for me to cram into 2 minutes right now. You guys have a beautiful weekend, and we will talk some more on Tuesday.